All right, we're good. Everything's working. All right, so before we start, are there any questions about the other stuff? Homework questions, things you want to go over before we start out and anything new? Okay. I know it was last week already, but if you ever do have questions on homework, you want to bring them in for the class. Probably other people have the same questions, so feel free to do that. But if there aren't any now, then we'll go on and talk about atoms and elements. Okay. So let's start with the periodic table. You see it over there, right? All those things stand for elements, of course, as you know. And today we're going to look a little bit more about how it's organized, why it's organized the way it is, and what we can figure out about things based on that. So you might want your own periodic table for this. If you have one in your lab notebook, or if you have a book with you, or on your phone. If you don't have one, if you want to grab one, there's some here. The only reason you'd want a different one from the one on the wall is the names. That one has the names. The wall one doesn't have the names. So just return this at the end of class. They'll always be here for you to use. And these will be the periodic tables that we use for the exam also. Quizzes. So you don't ever have to memorize names of elements. You will always have the periodic table with the names to help you. So if you want to memorize them, that's fine. You don't have to. I wouldn't. It's not worth your time. Don't worry about it. All right. So let's look at that. Let's look at the table. So I'm going to copy over a table from the book. There's a couple ways that we can think about how this thing is organized. One way kind of looks like this. From the book. One way is to group elements into groups where they have some similar properties, some similar things they do. And so here are some common names of groups of elements in the periodic table. On the far left, they're called the alkali metals, and that would encompass all of them except hydrogen on the very top. Hydrogen's kind of special. Then next we have the alkaline earth metals. The whole middle block in the middle is called the transition metals or transition elements. Then you've got this kind of other area that do have some common names, but they're not as popular, so we won't worry about them here. And then the halogens in 7A and the noble gases in 8A. So you should know those names because we'll talk about them and we'll refer to things by their names. We'll say things like, well, this rule applies to the alkali metals, but not the transition elements and things like that. So you should know these groupings, these common groupings. So one thing that comes up from this then is that one thing you might see is that elements that are on top of each other tend to have somewhat similar behavior. And that's one part of the periodic table that's very important. So we have a name for this. If you look down a column, we call that a group, or sometimes a family, but generally a group. And you see it written right up on the big periodic table there. The group is going down. So elements in the same group are going to have some similar properties, maybe some similar ways that they react, some similar stability, things like that. And then what gives rise to that is what we call the periodic behavior. So if something is periodic, it means that it happens regularly, like on a cycle. So in this particular cycle, as you go across the periodic table, that's known as a period, because then when you are back here again, you're back in the same group. So if we say that everything in the alkali metals is the same or has similar properties, we go alkali metal, alkaline earth metal, some stuff, some other stuff, and then we're back to the alkali metals again. So that's this idea of this periodic behavior. And in a little bit, we're going to look at the electrons in atoms and actually figure out why that is, what's going on inside the atom that causes that behavior as you add these numbers up. So that's one way to look at the periodic table, is by grouping them into these particular groups. There's another more general grouping that you should know as well. And that's this one, so we'll put this one in there also. Besides all those little named groups, we can also group the elements into 3 categories: metals and nonmetals, and then these kind of in-between things called metalloids or semi-metals. So sort of in the middle. Let's think about what that means for these elements. Well, what are some properties that you know of metals? What do metals do? What are metals like? Is what? Yeah, they're malleable. What does that mean? Yeah, they can be formed or bent without breaking. So have you ever just like taken a big hammer to the side of a car? Something you don't like or anything? Okay, try it sometime. Don't try it sometime. It's probably very cathartic, but you shouldn't do it. But what happens if you take a hammer to the side of a car? It dents, right? What happens if you take the hammer to the window? It breaks, it shatters. Has anybody ever done that? A little bit of both? Okay, yeah, you seem like a hitting cars with hammers sort of guy. I don't know what that means, I'm sorry. But yeah, so metals, what happens, it has to do with their electronic structure, that when you move the atoms around in a metal, the electrons can fill in the spaces and kind of make that okay. Whereas in a non-metal, the electrons are bound really tightly with the atoms, and so they break apart. So that's one difference between metals and non-metals. And the word that we would use for the non-metals is brittle. We would say rather than being malleable, they are brittle. So they break apart, kind of shatter instead of bending. So yeah, that's a good property of metals. What else? What else are metals like? Would you know if you saw something if it was metal? Unless I was trying to trick you or something. What?
Not necessarily. You might want to probably have a better indication if you felt it would be.
Okay, so what do metals feel like that's different from non-metals?
When you feel they're usually cool.
Yeah, why do you think that is?
They have a high heat. What's it called?
Yeah.
I forget what the term.
The specific heat.
Specific.
Yeah, and it's low actually. So which is related to, but not exactly the same as another property called thermal conductivity. So how quickly it conducts heat. So like a piece of metal feels cool because it's actually the same temperature as the room, and it conducts heat so quickly that it pulls heat away from your hand. So it's almost like an endothermic kind of a behavior where it's pulling that heat away because it can conduct heat so well. So that's another one. We can say generally metals are going to have low specific heat or thermal conductivity. Another one, I don't know if anybody ever noticed this, but they're shiny. So you can look at a metal and it usually has this reflective kind of surface that is unusual in other kinds of compounds. It's not impossible to obtain in other kinds of compounds, but it's usually associated with metal. And then the last one, one more property of metal that's important. I want to try to throw another one out there. What else do metals do that other things really don't? They melt. I mean, other things melt. You're right. I mean, yeah, they conduct what? Electricity. That's the other big one here. Now that's something you can't tell by looking at it. You'd have to test it, see if it runs an electric current through it or not. But most solids that pass electric current, or many of them, are metals, especially if they pass them with very, very little resistance. So nonmetals are going to be just the opposite of these things. The specific heat issue is, so the nonmetals are going to have a higher specific heat. Generally, that's not always the case. It also has to do with their state. So I don't know that that's a great one to remember, but nonmetals are usually dull in luster. They don't have that shininess to them the way metals do. And they're usually insulators, which is the opposite of conductors. So they prevent the flow of electricity instead of facilitating the flow of electricity. Okay, so we've got properties of metals and nonmetals. What about this strange little band in the middle, the metalloids? What do you think they do? If you had to guess. Like, okay, let's just pick a property. Let's take the last one. So we say metals are electrically conductive, nonmetals are not electrically conductive. What do you think metalloids are? Yeah, they're like in the middle, right? So metalloids pretty much are in the middle of all these properties. They have some characteristics of one and some of the other. And in fact, for that particular one, conductor, as you said, we call those often semiconductors, if you've heard that term before. Microchips and things like that are made out of silicon and germanium, generally, which are right on that line. And the property of being only sort of good at conducting electricity turns out to be really important for that, because you can add other chemicals to them and then create these junctions so that electricity only flows in one direction. And anyway, there's a whole thing, but that's why those things work. So we're not going to list any specific properties of the middle ones. They're just kind of in the middle. All right, so if you need to place an element or classify an element as either a metal or a nonmetal or a metalloid, how would you do it? Like if I throw one out there like sulfur, S, and you didn't have this nice color-coded chart, how could you remember which ones are which? Any ideas? What? Oh, I meant just like looking at the periodic table. So if I just said like S, which is number 16, how would you know that that is in the yellow in nonmetals if you didn't have this chart to look at? Yeah, that stair step thing. So you see that's highlighted on the periodic table. It's highlighted on most periodic tables. That kind of steps down, starting underneath boron B, and kind of goes down that way. Any element that's touching that stair is a metalloid or a semi-metal, except aluminum. But we know aluminum is a metal, like aluminum foil. So we usually don't mess that one up. But the other ones are all these semi-metals. And then anything on the left is a metal. Anything on the right is a non-metal. So if you get confused by that, just remember that there are these pretty big categories. And if it's in with something you know, then it's got the same thing. So if I ask you about ruthenium, which is number 44, and you don't remember which side the metals are on, well, ruthenium is right underneath iron. And we can probably all remember that iron is a metal, because that's what we make cars out of and stuff. So ruthenium's on the same side, so it's also going to be a metal. So metals on the left, non-metals on the right, metalloids in the middle. That's another way to classify elements in the periodic table. All right, so that's basic periodic table classification. Any questions about that? We should also note these bottom two rows, the lanthanides and actinides. You can never see how those fit in. If we follow the numbers over here, so we go 54, 55, 56, 57, and then it jumps down here to 58. So how this should really look is that should actually be stuck right in the middle here. So you should separate this whole thing apart and stick those two lines in right there. But that would make for a really awkward long table. And so we kind of take them out and put them down here. But if you follow the numbers, it goes 57, then 58, through to 71, and then right back there to 72. And these are called the lanthanides and actinides. You don't need to know those names. But if you've ever heard of rare earth elements, like rare earth magnets or things like that, that's all these right here in this top row. They're not actually that rare. It's not a great term, but that's what we call them. They're radioactive. No, so the ones that have an outline here are radioactive, but that includes some up here also. You'll notice they also have their mass in parentheses, we'll talk about later. Yeah, the outline ones are radioactive. The, I'm sorry. There's a lot of them that are radioactive. The outline ones are man-made, meaning they don't occur in nature. The red ones are gases, the blue ones are liquids at room temperature. All right. So now that we know some things about the periodic table, let's talk a little bit about those numbers that we see in the periodic table and what they mean and what they don't mean. Well, we're going to talk now about what atoms are made of. There's a whole kind of part of your book about the story of atomic theory and how we, or how people eventually figured out that atoms are, or that stuff, matter is made up of atoms. We're not going to go through the whole story. Go ahead and read it if you want, but we're going to focus on the results of that story, which is what's going on inside the atom. So we say that the smallest unit of matter is an atom, but atoms, of course, also are made up of things. What are atoms made up of? Protons, neutrons, and electrons. Anything else? You're right, that's all. So we've got protons, neutrons, and electrons. Let's talk about each of those. So we'll start with protons. What do you know about protons? Okay. Yes, but what about the protons themselves? So we'll get to that in a second. You're right. But yeah, they have a positive charge. This pen's being a little weird again today. We'll have to restart this thing at the break. So they have, we say that they have an electrical charge of +1. That's not actually in electrical units, but relative to the other particles, they're +1. Anything else we know about them? Yeah. Yeah. Their mass is 1 AMU, or approximately 1 AMU. AMU stands for atomic mass unit. If we weighed something as tiny as a proton in grams or kilograms or even micrograms or nanograms, it would be still much smaller than that. So we come up with a new unit called an atomic mass unit, AMU, and we define it as 1/12 the mass of a carbon-12 atom. So it's really just an arbitrary unit to say, to make it so that protons and neutrons are each about 1. So they weigh about 1. And in a future chapter, in chapter 7, I think, we'll talk about how atomic mass units relate to grams in a useful way, but we'll get to that later. All right, so protons have a positive charge and a mass of 1 AMU. What about neutrons? No charge, right? So they are not charged. No electrical charge. What about their mass? I think I just said it. They also are 1 AMU. And then what about electrons? Negative charge. So a charge of -1. And what about their mass? Yeah, it's actually so small that we'll say that their mass is negligible, which just means that we can ignore it. We don't have to think about it. So it's not right to say that they have no mass. They have mass, but their mass is so many orders of magnitude smaller than protons and neutrons that it doesn't really contribute to the mass of the atom. So we don't worry about the mass of the electrons. All right, so those are our basic particles. Where are they located in the atom? Yeah, so we've got the protons and neutrons in the core, or what we say the nucleus. So the center of the atom is made up of the protons and neutrons. Okay. And it's very small, tightly packed area. And then the electrons are around the outside. And we have to be a little bit careful about how we describe what's going on with the electrons in the atom. So you may, well, I'm sure you've seen kind of the classic model of the atom, which kind of looks like a solar system, where you've got the nucleus in the center and you've got the electrons going around like planets around the center. That's not really how it works. Electrons don't travel in predictable orbits like that, where they follow a particular path around the nucleus. It's better to say that the electrons kind of exist in clouds outside the nucleus. So they're just sort of there. They're somewhere. We're not sure where they are, but they're there. We know from like a probability sense that they're more likely to be over here than over here in certain parts of the atom. But we can't say specifically that they follow a path or that they're in this specific place in the atom. So the nucleus is in the center. The electrons are around the outside, but they're not orbiting around the nucleus. And in fact, they're pretty far away. So the diameter of a nucleus, and this is different depending on atoms, but the diameter is around 10 to the minus 15th meters, which is very, very small, of course, a tiny, tiny diameter. If you're not familiar with scientific notation, that's like saying 0.000, 14 zeros, and then a 1 meter. So extremely, extremely tiny. But of course, atoms are also tiny. So the diameter of an atom is about 10 to the minus 10 meters. Okay, so also very tiny. Neither of those sizes are anything we can really deal with because it's just too small for us to understand. But we can look at the comparison and see that. So we're saying that the nucleus, if the nucleus is about 10 to the 5th times smaller, than, which is 10,000 times smaller than the overall size of the atom. So we can, if we put that into terms, we can understand if we scale this up to 1 meter, if our atomic nucleus is this big, this is the diameter of the atomic nucleus, then the atomic radius of the whole atom is 10 to the 5th meters away, which is 10,000 meters or 10 kilometers, so about 6 miles. So if this is our nucleus, then that means the electrons are, where is that, this planes or something? Depending on which direction you're going. So like you could get a sense that the nucleus is very small and compact and the electrons are pretty far away. So most of all matter is just empty space, really, because in between that stuff. Think about that next time you're on a bridge. All right, so that's our atoms. So we can use the periodic table now to figure out how many of some of these particles are in an atom, but not all of them. Not all of them. So let's define ourselves some terms here. Let's see if I can get this thing to work better. We're going to define 3 different terms or phrases that are kind of similar, but it's important to try to keep them straight. So they are these. The atomic number, the mass number, and the atomic mass. Okay, so those all have some similar words in them. They're not the same. The second 2 in particular are easy to confuse with each other, so we're going to make sure to get them straight. So first of all, the atomic number. What is that? Anybody know where that is in the periodic table? Yeah, it's the top one in blue. It's not always in blue, but it's usually on the top in most periodic tables. It's above there. The other way to tell is that it's the whole number, the big, nice whole number that counts up as you go through the periodic table. So starting from 1 on the upper left, the atomic number increases as you go through the periodic table. So we'll say the top blue number, even though other periodic tables, it may not be blue, but we can always refer to our big room periodic table for that. So it's the top blue number. And what does it tell you? Yeah. So that number gives you the number of protons, which tells us that the number of protons identifies the atom. So if you have 6 protons, that's C. If this atom has 6 protons, it is a carbon atom. Any atom with 6 protons is considered a carbon atom, always. If it has more than 6, it turns into something else. If it has fewer than 6, it turns into something else. So that always goes with the identity of the atom, how many protons it has. The other things can change. So there can be carbon with different numbers of neutrons. We'll talk about that. There can be carbon with different numbers of electrons. We'll talk about that. But if it has different numbers of protons, it's no longer carbon. All right. So let's look at the mass number. These two are easily confused because of whether they are or are not on the periodic table. And so the first thing with the mass number is that it's not on the periodic table. The mass number is the number of protons plus the number of neutrons. So just the number of the two added together. We call that the mass number. Now you cannot figure that number out from the periodic table. That is not a number that is related to, like, as an internal property or an intrinsic property of an atom. I can't ask you, what is the mass number of carbon? Because actually there are different kinds of carbon, and there's carbons with different mass numbers. So this is a number that you have to be told. That has to be specified. Which mass number are we talking about? And we're going to do some practice to look at that in a minute. The atomic mass, then, is the number on the periodic table. And I'm going to define this with some terms that we haven't defined yet, but we'll get to that later. The average mass of all isotopes. Isotopes are atoms with different numbers of neutrons. So if we say, for instance, carbon, there are some common different forms of carbon. Carbon 12 is the most common. That's a carbon with a mass number of 12. But there's also carbon 13 and there's also carbon 14. Those all have different mass numbers, 12, 13, and 14. But we average those together to get the number that you see up on the periodic table, which is why those are all decimal numbers, because they're actually averages of the masses. It's really tempting, and I see this all the time on quizzes and exams. If I ask you, like, what's the mass number of something, and we'll do a practice like this in a little bit, rather than use the numbers that are given, it's tempting to look up on the periodic table and say, oh, okay, it's about 28, so it's probably 28. That's not right, because remember, those are averages. Those are not the specific atoms that we're talking about in the problem. So we're going to practice now a couple things to try to keep these things straight. All right. When we write the symbol for an atom, of course, depending on what we're doing, we will usually just write the symbol as it appears on the periodic table. But if we want to specify a mass number, we can do that by putting it in the upper left-hand corner. So if we write a C with a little 12 in the upper left-hand corner, we are specifying that this is carbon with a mass number of 12. And once we're given that number, now we can figure out how many of the different types of particles there are. So what's how many protons are in this atom of carbon 12? 6. How do you know that? Right. So you look the symbol up on the periodic table, and whatever the atomic number is, that's how many protons there are. So it's C, it's 6. So this tells us 6 protons. Okay. How many neutrons are there? Also 6. How do you know? Right. So the mass number is the protons and the neutrons added together. We know that that's 12. So that tells us that if there's 6 protons and the protons and the neutrons have to add up to 12, then there's got to be 6 neutrons. What about electrons? How many electrons? How do you know 6? Or are you just following the pattern? Yeah, if we're talking about a regular old atom, and we'll get into ions in the next chapter, but if we're talking about a regular old atom, it has to be neutral, which means it has to have no charge overall. And that means that all the positive and negative charges have to balance. There has to be the same number of positive and negative charges. So we've already said that there are 6 protons, which tells us 6 positive charges in this atom. So for it to be neutral, there need to be 6 negative charges also to balance this thing out. So we can say there are also 6 electrons. All right, so that's how you figure out all of the subatomic particles of an atom. To try this, we're going to grab a problem from the book. I like the way these are laid out because we can do a bunch of them at once. All right, so we're going to complete this table using those same techniques that we just worked on. In each case, you're given some information, and you have to figure out the rest of it. So let's do the first column together, or the first row together. So we're given the atomic symbol. The upper left-hand corner tells us 34. The lower left says 16. What is that? Kind of. Yeah, it's the atomic number. So sometimes the atomic number is written in the lower left. It's redundant because just being told S, we know it has to be 16. Anything that's sulfur is 16. But we could put the number there just to be extra specific or to make it really, really clear what we're talking about. So that's what that 16 is. All right, so given all that information, we should be able to figure out the name, the number of protons, neutrons, and electrons. So first, the name. How do we get the name? You look it up, right? Yeah, look at your card, look at your periodic table. What do you find? Sulfur. Sulfur, yeah. Now, as we get going through the semester, you will, you know one of those? Yeah. You'll probably pick up on some of the ones that we use over and over again. But you don't have to memorize them. And it's always a good idea to look them up in an exam because you've got them there. There's a lot of elements that have pretty similar names. There's ruthenium and rhodium and radium and rubidium and I don't know. There's thorium and thulium and thallium and titanium and tantalum. So like, if those things come up, just look them up. You know, you don't need to impress anybody. Just look it up. All right, back to this then. Sorry. We've got our name. We've got our symbol. How many protons? We already talked about that. 16, right, from the atomic number. How many neutrons? Yeah, 18 in this case, because the mass number is 34, and the protons and the neutrons have to add up to the mass number. So that means we've got to have 18 neutrons, because 16 and 18 is 34. Okay. It's tempting sometimes to see that this is sulfur and immediately look up on the periodic table and see that the red number is about 32 and think that you got to use that. Use the one that's there. Use the one on the symbol. It's 34, so it's got to be 16, 18. And then the number of electrons, as long as it's a neutral atom, which all of these are so far, has to balance out and equal the number of protons. So we'll have 16 there also. Those will always balance out for a neutral atom. All right, so see if you can fill in the rest of that table. And then we'll go on. Oh, you're stuck. So let me go back up to the definitions here if I can get them all on the same screen. There we go. So remember, we're getting the number of protons from the atomic number, the mass number from the, or I'm sorry, the number of neutrons from the mass number, and then the number of electrons are going to be the same as the number of protons. All right, let's take a look at it. Don't worry if you didn't get it finished. There's lots more of these in the book and lots of practice. Let's look at the next row. This one, we're just given the number of protons and neutrons, but again, that's all you need. You know the number of electrons is going to be equal to the number of protons, assuming it's neutral. And then we can look up the identity on the periodic table, figure out what it is. So 28 is nickel, right? All right. Now we got to fill in those symbols. The atomic number goes in the bottom 28. Another really common mistake is to put just the number of neutrons on top. Remember that it's the mass number that goes on top, which is the neutrons and the protons added together. So 28 and 34 is 62. Okay, so I'm going to put a 62 up there. Good so far? Questions? Is it not 62? No, it's good. All right, let's keep going. So the next one, we're only told the name and the number of neutrons. Doesn't seem like a lot of information. But remember, once we've got the name, what else do we know? The protons, because we can look it up in the table. So we look up magnesium, it's Mg, which comes out to 12 protons, because it's element number 12. That tells us it's also got to be 12 electrons, because those are always the same. And then our atomic symbol, Mg, and we'll put the 12 down there, because that's how they've been doing it. And that's going to be 26. Like that. All right, and the very last one, we can look up the name. This is radon. We got 86 protons from that bottom number. We've got 134 neutrons. Right? Did I do that math right? Okay. And then our electrons are going to be the same as the protons, 86. Okay, so make sure you can do that for the quiz on Monday and the exam on Wednesday, because that will definitely be part of it. All right, there's lots of practice on doing that throughout Chapter 4 and then in the back also. So if you have any questions with that homework, let me know. Oh, speaking of homework, the bookstore let us know that there are no more student study guide solution manual copies. I don't know if anybody still was planning on getting one, but if you are, you just have to get it online or something because they don't have it. Also, the student as we talked about at the beginning, that solutions manual doesn't include all the answers to the homework. It's only like the odd numbered ones. So if you want all of them, you can look for the instructor solutions manual, which is also for sale, but not in the bookstore. But you can probably find it somewhere on the internet. Or you can just come ask me, and I'll tell you. All right, moving on to the last part of Chapter 4 then, and then we'll take a little break. We're going to get away from the nucleus, and we're actually going to forget about the nucleus for a while. I mean, don't forget about it like the exam and stuff, but we're not going to worry about the nucleus too much. We're just going to focus on the electrons for pretty much the rest of the semester, because chemistry is all about the electrons. It's about how the electrons interact with each other, what the electrons do. And so we're going to look at now what we call the quantum mechanical model of the atom, which is a fancy way of saying that the electrons are arranged in different energy levels around the nucleus. Some are at lower energy, and some are at higher energy of different levels. So if you were to guess, what do you think is lower energy, meaning more stable? Electrons being closer to the nucleus or being farther away from the nucleus? What's like a happier place for electrons to be?
Closer.
Yeah. Why? Just a guess, or?
It's the hardest, I suppose.
Okay. Just
More
feels
structure.
right. Yeah. You're absolutely right. Does anybody know why? Why would the electrons be happier, more stable, lower energy, closer to the nucleus?
They're protected.
The what?
They're protected from the.
Kind of. Yeah. Yeah, it's really just the electrical charges. So electrons are negative, protons are positive. Positive and negative attract. So the closer positive and negative are to each other, the better. And that's why, so if you keep that in mind, that's the most important thing about the electron energies, is that the ones closest to the nucleus are the most stable, the lowest energy. And we can graph this on a special kind of a graph. There's lots of different ways to make these graphs. The book does it like, how does the book do it? The book just kind of has numbers. It doesn't even make a nice picture. So we're going to make nicer pictures. Yeah. So the book just has numbers. We'll make pictures, but there's various pictures. You might have seen what we'll see in lab on Wednesday also is you have the nucleus in the middle, and then you have electrons on these different shells outside of the nucleus. That's one way to do it. I don't like that method as much because it reinforces that idea that the electrons are in these circular orbits, which we know is not right. So we're just going to think of it on a graph as energy levels. So our y-axis is going to be energy. And the x-axis is going to be level, or we can also think of this as distance from the nucleus. So we're going to look at 3 levels, 1, 2, and 3. And we're going to say 1 is the electrons that are closest to the nucleus, and then 2 they're a little further away, and then 3 they're a little further away yet. And the central point of the quantum model of the atom, or the idea of quantum mechanics, is that electrons can't just be at any energy. They have to be at specific levels, and they can jump from level to level. We'll see this in some experiments. This is set up for the lab, so we'll see this on Wednesday. But when electrons jump from level to level, they have to absorb or give off a certain amount of energy. They can't just take whatever energy there is. It can only go from this level to this level. So they're kind of stuck on these specific levels. That's this idea of quantized energy levels. So we're going to say that on these 3 levels, electrons can only be in one of 3 places here. The first level, which we're going to make is kind of like a little bucket to hold electrons. So that's my electron bucket on the first level. And it holds 2 electrons. But it has space for 2 electrons in there. The second level is going to be higher in energy, further away from the nucleus, and it can hold more electrons. So the second level holds, stick with the same color here. The second level holds 8 electrons. And then the third level is a little bit higher. We're going to say it also holds 8 electrons. Now, if you've done some chemistry before, or you go on, you'll learn that the third level is actually bigger and holds more than 8 electrons. It can actually hold 18, but it starts to get tricky. And for the ones that we're going to look at, we're going to focus on just the first 3 and just the ones that can hold up to 8 electrons in the third level. So this model will work well for our purposes. So what we do with a model like this is we use it to figure out how many electrons are in each level for a given atom. And that's why we had to do this particle counting, because we need to know how many particles there are so we can figure out the what we call the electron configuration of an atom. So let's pick one. Electron configuration of, let's stick with carbon, because we've been using that as our example. So if you want to know the electron configuration of carbon, what you do is you set up an empty set of buckets. Okay, in levels 1, 2, and 3. And then you fill them until they're full, and then move on to the next bucket with however many electrons you have. So if we're dealing with carbon, how many electrons do we have to deal with? 6, right? So we start counting up our 6 electrons. 1, 2, 3, 4, 5, 6. We're done. So we would say that a carbon atom has 2 electrons in its first level, or its first quantum level, and 4 electrons in its second level. And that's it. Not too bad, right? Just fill the buckets. All right. There's a couple other words that we want to use to describe the electrons in this bucket, and then we'll see why that becomes important. First one is called the valence electrons. The valence electrons are the ones in the highest bucket. They're important because they're the electrons that actually do all the chemistry. When we start talking about reactions and bonds and all of this other stuff, it's the valence electrons that are actually doing stuff, that are going out and making their connections. So they're going to be the ones in the highest energy level. So which are the valence electrons in carbon? Which ones are in the highest energy level? The 4 in the middle, the 4 in number 2. Do you see that? So those are our valence electrons for carbon. Anything that is not a valence electron is called a core electron. And the core electrons are so tightly held by the nucleus that they don't really participate in chemistry. They don't make bonds. They don't lose, get lost. They don't really do anything. They're just kind of part of the atom. They're just really stuck there. So we don't worry as much about them. So it's important, as we'll see in the next chapter in a little while, it's always important to know how many valence electrons an atom has. And we figure that out by doing the buckets or by some shortcuts that we'll talk about in a second. So let's see if you can do one more. Create and determine the electron configuration of silicon and figure out how many valence and core electrons it has. So silicon is Si. Do the electron configuration, and then determine how many valence electrons it has and how many core electrons it has. When you think you've got it, ask somebody around you at your table and see if you came up with the same thing. So if you're stuck here, remember the first thing you do is look up the number of electrons, which is going to be the same as the number of protons. And then start filling up those buckets, 2, 8, and 8. So All right, lots of good buckets there. Don't worry if you didn't get it yet. We'll take a look at it. So we're going to come up with the same thing. There's our 2 bucket, our 8, and our 8. We look up silicon on the periodic table. We find that it's element number 14. So that tells us we have 14 electrons to deal with. All right, let's start counting those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that fills up my 8 bucket there. So then I've got to go 11, 12, 13, 14. So that works? Okay. So now let's look at those definitions. How many valence electrons are there here? Yeah, just 4, just the outermost level. So we've got 4 valence electrons. And how many core electrons? 10, right, because remember, all the rest are core electrons. So all of these are core electrons, so are 10 core electrons. Okay. Let's take a look at this and look at why it's such a good model now. So we did our electron configuration over here for carbon, and we came up with 4 valence electrons. We did a configuration for silicon, and once again came out with 4 valence electrons. Where are carbon and silicon on the periodic table? In relation to each other? They're right on top of each other. They're in the same group. They're in the same group. And we said that valence electrons determines the chemistry. And groups, vertical groups in the periodic table have similar chemistry. That all kind of makes sense. So if we know the valence electrons, we can predict some things about the behavior. And that's what we're going to see in chapter 6. And the best part of it is there's a great shortcut. Because what column number is that carbon and silicon are in? 4A. Everybody see that? 4A. So you can actually use those numbers to figure out the number of valence electrons without doing the buckets. Everything in 4A is going to have 4 valence electrons. Everything in 5A is going to have 5 valence electrons. 6A is going to have 6, and so on. The only thing is it only works for the A's. It doesn't work for the B's in the middle. They're kind of weird. Does anybody remember the name for that group in the middle? All the B's? Yeah, the transition element. So it doesn't work for those, but everything else it works for. And the bucket thing only works for the first 3 rows, because it gets weird after that. But the column thing works all throughout. So even though an atom like, let's say iodine, number 53, way over here, is way down in the 5th row, so it would actually have electrons out in some sort of 5th bucket that we're saying we're not going to do because it doesn't quite work right. But we can still say that it has 7 valence electrons in that 5th bucket, because it's 7A. So that makes things really predictive in it. And when we look at compounds in the next chapter, it will make a lot more sense when we can organize things that way. Because as soon as we know what kind of compounds one thing makes, we can make a pretty good guess that the other things in that column are going to do the same thing. All right, any questions about that? Yeah. All right, so let's take 15 minutes or so, and then we'll come back and look at some ions and ionic compounds. And I'm going to restart the computer and see if I can write better.